Okay, sorry about that. Kind of got cut off and long-winded there, but nonetheless, let's pick up where we left off on talking about the simple regression example from Yaki chapter 13. So let's go back to our output and pick up where we left off. We just talked about the ANOVA. So now let's look at the coefficients table. We have on the left here two parts to the model. We have the constant, which recall is the y-intercept, and we have support, which is our predictor variable. Then under this column where we have unstandardized coefficients, this number here, 18.954, would be our y-intercept, and then this number, 1.023, represents our unstandardized regression coefficient. And recall that that tells us for every one unit increase in the independent variable, in this case support, we get a 1.023 increase on average of the dependent variable, which is well-being. And so this represents the slope of that best fit line in the metrics of the original measurement. Then we have a standardized coefficient here on this column. This is called the beta, and so this represents the change in the independent variable, one standard deviation change in the independent variable, how much of a standard deviation changes on average in the dependent variable, which is 0.49. And so this obviously is a little bit different. You also notice that there's a t-value here, so the test statistic here is a t, and t of 2.698 represents a significance, a p-value of 0.013. You'll notice that there's a exact duplication of what's in the ANOVA table and what's down here. So when you have a simple regression, the ANOVA table basically tells you, is that independent variable a good predictor of the dependent variable? In this case, we would conclude that that is indeed what's going on. So that gives us the analysis. Now, if we're going to put together a regression equation, we'll need two things. We'll need this constant, which is our a, or the y-intercept, and we'll need the b, which is our unstandardized coefficient. So we'll multiply that by x. So let's go back to the PowerPoint presentation and take a look at how we can use regression equation to make a prediction. And here we see that we've got our regression equation where we've got our predicted value of the dependent variable. We call that the y-hat, and then that's equal to our y-intercept, or a constant from that table we were just looking at, and the slope of the best fit line, and that's our variable x. So what we need to do now is to take the data from that table and insert it into this equation, and then we can actually come up with an estimate, a predicted estimate for the dependent variable based on the independent variable. So we can make a guess at what well-being would be if we knew what an individual's level of social support was. So in this equation here, we can see y-hat for well-being is equal to this 18.954 that came from the coefficients table, as well as this 1.023, which was our unstandardized b coefficient, and then we're going to multiply that by whatever the level of social support is. So suppose the level of social support is 20, so we would take that 20 and plug it into this equation right here. Go ahead and crunch those numbers. So take 18.954 and add that to the product of 1.023 and 20, and that comes out to be 39.41. So if I knew an individual's social support was 20, I could, according to this model, say with reasonable surety that I would expect something around 39.41 for that individual's well-being. So taking a look at the write-ups, this is the exact same, well, close to the same verbiage that Yaki used in the text. So we would say that a simple regression analysis, I put simple in red because I added that word to it because I think that helps to clarify things. So a simple regression analysis was conducted with well-being as the criterion variable and social support as the predictor. Then you go on to describe the actual statistics. So we would say social support was a significant predictor of well-being, and then we'd report the beta. Actually, Yaki does not include a digit before that, but beta weights can be more than 1, so I believe that he should have included a 0 there in front of the 0.49. And then we provide the T statistic, and remember in the parentheses here is the degrees of freedom. We had 24 individuals. We take off 1 for the comparison, so that gives us 23, and so that equals 2.70 as reported in the coefficients table. Then Yaki says P is less than 0.05, and as we've said several times, you need to report the exact P value, and that was available in 2 places, the ANOVA table and the coefficient table, so we're going to put that in there. Social support was a significant predictor of well-being. Beta equals 0.49. The T at degrees of freedom 23 is equal to 2.70, and P equals 0.013, and accounted for 24% of the variance in well-being scores. So that's our effect size, our R squared, so I can put that in text and then as well as parenthetically show what that actual value was. So that gives you an idea of what the write-up would look like, and then so that about concludes our discussion of Chapter 13 and the simple regression. Next we'll move on to multiple regression.